Welcome back to our discussion of limits at infinity, which I'll remind you are those limits where I have an x goes to infinity or an x goes to minus infinity, and only those. Any other limits, not at all relevant for this discussion. We talked last time about how to handle monomials and polynomials when we're calculating limits at infinity or minus infinity. And namely, we talked about how to figure out whether you got a plus infinity or a minus infinity, and it depended on only the highest power of x. And so the moral of last video was really that in a fight between a bunch of different powers of x, it's always the highest power of x that's going to win. That lesson is going to also dictate what's happening today when we talk about rational functions. And when someone says rational function, what they really mean is just function that's a fraction. So let me write down some messy-looking rational function. And so what's going to happen is that this same rule, that the highest power of x always wins, is going to apply, but it's going to apply separately in the numerator and the denominator. So I'm going to look here at the numerator. That's my highest order term there. I'm going to look here in the denominator. That's my highest term there. And so what does that mean? That means that this is going to behave exactly like the limit as x goes to infinity of 2x cubed divided by 5x squared. So the punchline is only the highest order term in the numerator and the denominator matters. So all of this junk does not matter. So I can rewrite this like this. And the cool thing is, once I've rewritten it like this, I can actually rewrite it even better. Namely, this is 2/5 times x. Because x cubed divided by x squared, that's x to the 3 minus 2, which is just x to the 1, which is just x. And so the question of what happened to this messy thing when x is really big has now been reduced to the question of what happens to this relatively benign thing when x is really big. In other words, if x is a huge positive number, what sort of number is 2/5 times x? Well, if x is a huge positive number, well, then x is a huge positive number. And so 2/5 of x is still a huge positive number. And so this is going to be plus infinity. Exactly the same thing applies here in the second line. Namely, I get to look only at the highest order terms. The fact that it's a minus infinity instead of a plus infinity doesn't change anything. So this will become the limit as x goes to minus infinity of 2x cubed over 5x squared, just like it did before, which will be the limit as x goes to minus infinity of 2/5 of x. And so now if x is a huge negative number, then x is a huge negative number, and so 2/5 of x is a huge negative number. Okay, and so we get that this is plus infinity, this is minus infinity. Let me make just the tiniest switch on this limit, though, and see how it works. Okay, so take a second to figure out that I really did change something. Namely, the thing I changed is that I swapped the 3 and the 2 in the exponents. And so I want to see what that does to the value of this limit. And if you want to make sure you're understanding everything, you can go ahead and pause the video and figure out what this limit is before we go ahead and do it. Okay. But what do I need to do? I need to find the highest order term in the numerator, which is this one, and the highest order term in the denominator, which is this one, and throw everything else away. And so this is the limit as x goes to infinity of 2x squared divided by 5x cubed. Okay. which is the limit as x goes to infinity of now 2/5 times x to the minus 1. Okay, minus 1, because I now have an x to the 2 divided by an x cubed, so it's an x to the 2 minus 3, which is minus 1. So what's this limit? Well, now I have to think if x is a huge positive number, what's x to the minus 1, or 1 over x if you want? Well, that's a very, very tiny number. And so, in fact, this limit is just 0. So be very careful, because even these two very similar looking questions have very different answers. To re-emphasize this point from earlier, here's another limit that looks a lot like the limit we were just doing. But there is an enormous difference. Namely, that piece. The fact that this is an x going to 1, rather than an x going to infinity or minus infinity, means that none of 2.3 applies to this limit. So in particular, I very much cannot throw away this minus 6x or the plus 7, or the minus 3x or the minus 9. I need all of those. And so I need, when I see something like this and there's an x going to 1, I need to make extra sure that I remember what I'm supposed to do. And now when I see x going to 1, I'm supposed to plug in 1 and get 2 minus 6, which is minus 4, plus 7, which is plus 3. Let's see, and so this is 5 minus 3 is 2, minus 9 is minus 7. And because this isn't 0 over 0 or anything like that, that lets us just skip straight to, okay, the answer is that this limit is minus 3/7. Okay. So again, be super careful, because it is very easy to accidentally start applying things where they don't apply. Okay, next up, let's look at this limit. So first of all, yes, it is going to plus or minus infinity, so I can go back to doing what we've been doing in this section. I now need to look at the highest order term in the numerator and the denominator. So this is the highest order term in the numerator. This is the highest order term in the denominator. Note the highest order term is not always the first term. It is just the highest power of x. And we've talked about how the convention is usually you write the powers in descending order. This is one of the reasons why, because then you could just always read off the top one, but they won't always be that way for whatever reason. So here, these are the two powers I want. Be sure you grab this minus sign, because this minus sign is a coefficient on the x to the 4th, so it's part of the term. And so, again, only the highest order terms matter, so these other two we can just get rid of. So I'll get a minus x to the 4th over x squared. This will be a limit as x goes to minus infinity of, and now x to the 4th divided by x squared, that's x to the 4 minus 2, that's x squared. So I have now that this limit that started out complicated is the same thing as this limit, which is now no longer that complicated. So if x is a huge negative number, what happens? Well, I square it and get a huge positive number. And then I negate it, and so I end up with a huge negative number. And so this is negative infinity. Okay. Again, reminder that when you see negative x squared, you don't read it left to right. You do the squaring first and the negation second. Because powers come before subtraction in PEMDAS, or whatever version, please excuse my dear Aunt Sally, or whatever version of this order of operations mnemonic you've learned. Okay, so we've got the limit as x goes to minus infinity of this. This is our last example of this flavor. So here's our highest order term in the numerator. Here's our highest order term in the denominator. So this is the same thing as the limit as x goes to minus infinity, minus x to the 5th, divided by x squared is the limit as x goes to minus infinity of minus x cubed. Okay, so now I have to think through this carefully. So if x is a huge negative number, then x cubed is a huge negative number because 3 is odd. And so I have an odd number of minus signs, and minus a minus minus, that's minus. Okay, so huge negative input, x cubed is a huge negative output. But then what does this minus sign do? It flips the huge negative output to a huge positive output. And so this limit is in fact plus infinity. So as a last example for this section, I want to point out that you can often use a little bit of algebra and a little bit of intuition to do some limits that don't originally look like limits of rational functions. So as my example, let's look at this. Okay. So this doesn't look like a fraction, but the reason it doesn't look like a fraction is because I've hidden the denominator up here as an x to the minus 3 in the numerator. So this is really the same thing as x goes to minus infinity of x plus 1 times 2x plus 1 times 3x plus 1, all divided by x cubed. So now I have to throw away all but the highest order terms. Okay. Well, the highest order term in the denominator is pretty clearly x cubed, because x cubed is the only thing in the denominator. And you might be inclined to think that in order to figure out the highest order term in the numerator, we actually have to multiply all of this mess out. Okay. But that sounds ugly, and I don't wanna. And so actually, you can figure out where is the highest order term going to come from. It's going to come from multiplying together all of these x pieces. So in fact, if you did multiply out this whole mess, you would get 6x cubed plus and then some other stuff that I don't want to calculate. Okay. But the 6x cubed, which I'm getting from 1 times 2 times 3, that's the leading term. That is the biggest term there. And so the limit as x goes to minus infinity of this quantity, it is the same thing as the limit as x goes to minus infinity of 6x cubed over x cubed, which is the same thing as the limit as x goes to minus infinity of 6. And so as x goes to minus infinity, what happens to 6? Or in other words, if x is a really enormous negative number, and I plug that into 6, what is 6 going to be? Well, it's still going to be 6. This is because there's no x's here, so what x is doing just doesn't matter. X could be literally any number, and 6 would, well, still be 6. And so the value of this limit works out to be, in fact, 6. All right, that's all for this video. In the next video, we're going to talk about section 2.4, and we're going to talk some about one-sided limits. But that's all for now. I'll see you all next time.